Okay, here we go. So we have two themes to talk about today. Soft and follow through. Now, both of these have to do with the impulse momentum theorem. So I'm going to write the impulse momentum theorem back up here, which was F times T equals mvf minus mvi. Okay, so let's start with this idea of soft. Now, let me throw out this question, have you think about this initially. If I were to give you a question to describe to me what is it about something that makes it soft, or what quality do all soft things have, what might you respond to that question with? Okay, Levi?
They're malleable.
Okay, now what do you now? Good vocabulary term. What do you mean by malleable?
You can shape it.
Okay, so if something gets hit with another object, that object, it kind of gives.
Yes.
Okay? Damn. Pretty much started us off right with what I was looking for. When an object is soft and there is another object that interacts with it, there is this ability for things that we refer to as being soft to like yield to the object that's hitting it. It deforms under the influence of that object. And that is going to be a key thing to keep in mind. I'm going to make up a really stupid example here to try and highlight this, at least as far as it relates to this. How many of you have ever thrown yourself onto a kind of a plush couch or, easy chair? Not like, oh, I got to be super careful. You can just let yourself go, because you're not going to get hurt, and it'd be like, it actually feels really nice. Okay? So I am going to try and attempt to draw a situation here of somebody doing that. So let's see, how am I going to do this? One, two arms. And I know that looks kind of big, but, and then let's see. And then we're going to do this again. All right, so now this will be the same, but this time, okay, we got a person, and literally we're going to say the exact same person kind of launching themselves onto a chair. Now, just based on the way I've drawn these pictures, which one's the soft one? Yeah, the one on that side, because it's nice and rounded off, okay? Now, we're going to go really extreme here. This is the soft chair. It's got memory foam, all that kind of plush stuff associated with it. This is like the Flintstone chair. It's like chipped out of granite. Okay? Now, in this impulse momentum equation, which side of the equation in this scenario is the person who's launching themselves onto the chair? Are they the force and the time, or are they the mass final velocity and the mass initial velocity? Any thoughts? Guesses? Bryce?
The mass side.
They're the mass side. Okay? Now remember the two words that I used to describe, like associated with this? I'm gonna, does anybody know what two words I'm fishing for when it comes to how this works? One of them started with an A, and the other one started with agent and object. And remember, the idea was the agent is the thing that brings the force and the time to act on the object. And because the agent does its thing, it causes a change over here in the motion of the object. So, if the person here is our mass in V, which of the two is the person? Somebody. Which of the two things is the person if they're this side?
The mass.
I'm looking between the two words, the agent and object.
Oh, they're the agent.
This side is the object. This is the agent. Where is the agent then here?
The chair.
The chair. Okay? So, I'm throwing a bunch of stuff out there. We'll all tie it together here. So, the person launches themselves onto the chair, and most people would not get this technical. They just say, oh, well, the person launches themselves onto the chair. They're going to land on the chair, and then they're going to be brought to rest. And you probably could say, well, what makes them come to rest? And they'd say, well, the chair. And that's the indicator that the chair is the agent, because the agent is the thing that brings the force into the situation to create an impulse, and the object is the thing that that impulse acts on to somehow change its motion. And in our case here, here's what I want to highlight. Let's start with this MVF MVI. First, let's say we have the same person doing this thing. If that's the case, what two variables would be what variable would be the same for both of these situations? If we have exactly the same person.
Mass.
The mass. So the m's in this scenario are exactly the same in both situations. If they have thrown themselves equally over to the chair, what else would be the same in both situations?
The initial velocity.
The initial velocity. So they're both going equally as fast. Now if you're going, oh, that's not going to go well for this guy. Granted, you're correct. But we're going to talk about how do you explain in terms of physics why it's not going to go well for him. The VI and the VI here are exactly the same value. What else is going to be the same? After they hit the chair, how fast are they going to be going? You can do this. 0. Because the chair is going to bring him to rest. Now again, if you're going, yeah, but this guy's going to feel a lot better than this guy. Yeah, but what we're trying to do is explain to you why is that from a physics perspective. So by talking about these things individually, what did we discover or uncover about the right side of this equation for both of these situations? If we put all this stuff that we just finished discussing about together just for this side of the equation, they're exactly the same. So this side of the equation for these two people is exactly the same. They are going to undergo the same change in momentum because they're coming in with exactly the same velocity, and they're both going to be brought to rest. Now we come to, well, then what's the difference? Okay? So what I'm going to do here is we're going to bring in the other side of the equation now. And we're going to talk about the F and the T, which is where we are talking about the agent now, not about the object. Now, just by describing this being like chipped out of granite and this being nice and soft and pillowy, most people already are going to say, this one's going to hurt and this one's not. So now we come to this side of the equation. We only have two variables, F and T. Which one of those would you say is the variable that is most directly related to whether somebody, says, or whether they're going, oh, that hurt? Which one of these two is most directly related to that sensation? The force or the time? If I come up and punch you and kind of go, and you're like, and then I go, yeah, and it's like, oh, which one is that? It's the force. So when someone says, that hurt, that usually means that the force that was acting on you was big enough for you to say, that hurt. So over here, how does the force here compare to the force here? Just because we know how things are going to feel. Which one's bigger? Okay, we're going to do this all with fingers today, like kind of like one on that side. Yeah, this one's going to be big. And this one is going to be smaller. But remember, what was true about this and this in both situations? They were the same number. Now, here you're probably like, oh, you are all over the place today, Mr. Penovich. We're going to go to math for a second. I think I'm still on camera. I'm going to make two different, actually I can do this top-bottom. Let's say I know that I'm going to have a product and it's going to equal, what's a good combination? Yeah, we could do. They're both going to equal 12. And I'm going to have two numbers being multiplied by each other. But what I know is that one of the numbers here is a big number. Let's go ahead and say it's 12. And this number is not going to be as big of a number, so let's call it 3. Okay? Without giving me an actual number at the moment, how is this number here going to compare to that number there, just in general? And let's call this number A and this one B? You don't have to give me the number, but just conceptually tell me, how will A and B compare to each other? Okay, somebody. Okay.
Number A will be less than number B.
A is going to be smaller than B. Okay? So let's come over here. This number here, whatever it is exactly the same number as this here. We know that this is going to hurt. And that means the F has to be really big here. We know that this one is going to feel nicer, and that means the F is going to be smaller there. But what's the variable that goes here in both equations? A time. How does this time here, because of this relationship, compare with the time that we would figure out here? And you can talk about the time on the left and the time on the right on this one. Are they going to be the same value? No. So tell me a little bit more about it then. Anybody? Okay, Julian?
Would the time on the left be less than the time on the right?
The time on the left is going to have to be less than the time on the right. So I would make this, a small size t. This one is going to be a bigger t. So why is it that this t is bigger than this one, besides the fact that I made it bigger? And this goes back to Levi's comment. What did this nice, soft, plush, pillowy chair do that the rock-hard granite did not? Right. When this person hit this thing kind of like molded around it, and it kind of enveloped, and it gave. And this person like sunk into it. What'd this do? Basically nothing. Okay? It's rock solid. So when we look, how many of you have ever done a video in slow motion? Okay. So if we were to say, let's pretend we're taking a video of this, which would take the most frames to video the complete bringing to rest of the person? The one on the right or the one on the left? The one on the right. We would be watching this chair like start to give, and the person would really sink into it, and we'd still be watching frames as it kind of went deeper and deeper. This guy here, we'd go through a couple frames, we are done. And because this had the ability to give, that means it takes longer for this person's momentum to be brought to zero. And because it takes longer to do that, that means the force that acts on the object is a smaller number than over here where you hit the rock, where your collision is over in a fraction of that other time. But because of that, the rock is pushing with a much greater force on you to make that same change in momentum happen. Okay? So this is my like stupid example for anything that is soft. And let me throw this out first before we start to talk about examples. Can somebody give me a parallel example of this in something that you're familiar with, where there is a specific application where you need something to be soft, and when we would look really closely, we're like, well, yeah, the material is designed to actually give or yield. I'm curious if anybody thinking about it would say, oh, wait a minute, I think I know something. Because I got a few examples that I want to share with you, but I want to see what if you kind of connect with anything. What do you got, Maria? Okay, your bed or your mattress. That one people really throw themselves onto sometimes. I remember bouncing on it, being a kid, going up onto my parents' bed, just using it like a trampoline. And people are usually not worried about it. Oh, damn. Did I have... Oh, okay. I mean, I'm not going to show this thing. I don't think I'm going to show this thing on the video, but I'm going to show you guys a video at the end that's, I find it hilarious. Can anybody think of another example of this? If you never really thought about it, you'd be like, I don't know. Who's into cars? Okay. Does that help at all? Cars.
An airbag?
Airbag. Good job. You're driving along. All of a sudden, you crash. What is it if you're the driver, you know, and usually this is presented in terms of like a head-on collision. You are brought to rest pretty suddenly. Now, that's not really this, but what tends to happen when that happens quickly? What does your body do? It goes forward, and if you're the driver, what's going on here? That's not going to be good, that you would run into. The steering column. Okay, we do have seat belts and all that to try and help us a little bit, but you are still kind of going to get thrown forward. And in that scenario, you are going to hit the steering column, which is a decently solid object. So somebody came up with the idea of, well, why don't we do an airbag? So the airbag deploys. All right. For those people who are out in video land, you just lost about 5 minutes of our discussion here because the iPad maxed out on its storage and shut down. So we were on the process of linking this concept to the idea of a helmet. And in a helmet, any helmet has kind of a hard exterior, and then it has a softer kind of liner. And the idea of the liner serves the purpose of this softer, pillowy chair, that if your head ever hits something, technically the helmet will be brought to rest very, very suddenly, but as your head presses into the liner will deform, and that ends up, again, from the physics perspective, extending the time of collision. And if the collision time gets bigger, that means the force involved does the exact opposite thing, and it gets smaller. Oh, now to bring in another math term. What do they call it when two things are related in such a way that if one gets bigger, then the other one gets smaller? I word? What? Nothing? Inversely related? When two things are inversely related, they do opposite things when they change. If one gets bigger, the other one gets smaller, or vice versa. And in this example, our force and our time are inversely related to each other. So if there's a way that we could make something take more time, that means the force would do the opposite thing and get smaller. And in terms of having something be soft or having something be safe, we want that F to be as small as possible. And many collisions that happen in our day-to-day life happen very quickly, so it's not like you have to have it end up taking a ton more time. You just somehow have to slow the process down. And if you got really technical, the idea is you could slow it down by a factor of 10 so that the time for a collision takes 10 times longer. That means the force would be reduced by a factor of 10, which means you could divide it by 10. Now, does anybody know of another safety feature on a car? It's actually built into the car itself. What? Okay.
The headrest and back.
Well, the headrest is more for inertia, so that your head doesn't snap back. But
Is it how like the front collapses?
yes. Anybody know what that's called? This used to be a bigger deal when I was growing up. They're like, ooh, these cars are designed with this thing. Now it's kind of standard.
Is it called a crumple zone?
A crumple zone. It's a place or sections of your car that are designed that if you get into an accident, they will actually give and crumple, and that does the same thing as what the liner does in the helmet. It extends the time of the collision so that the amount of force that ends up being transmitted to the people in the car goes down. The one bummer is, what does that mean about your car? It's more likely to have more damage sustained because of the fact that there is this weak spot. Anybody really watch NASCAR, IndyCar racing? If you, for example, with NASCAR, if you ever look inside, the chassis is really, really lightweight. So when things get into collisions, crap falls apart like super easily. But if you look inside the car, the main area where the driver is has all this heavy duty tubing that's welded together, and that keeps the driver safe. But the rest of the car is designed in such a way that when they get into accidents, sometimes the accidents look pretty impressive because crap flies all over the place, but that's actually not such a bad thing because that's part of the extending the time of the event out. Yes, Maria? Yes. Okay. I'm trying to think of anything else. Oh, how many people send packages? Ever send anything fragile? How do you keep it from breaking? Bubble wrap. You get the idea. What would most people say if they were to say, well, what does the bubble wrap do? What word would they use?
Pops.
What?
Pops.
It pops? I'm thinking of a C word.
Cushion.
It cushions something. So like if you drop it, they'd say, oh, it cushions it so it doesn't break. But when you think about, what does that cushion mean? Box hits the ground. The box is going to hit a pretty solid thing. It is going to be stopped pretty suddenly. But inside the box, that bubble wrap has the give, just like the liner of the helmet. So when the box hits the ground, the object will kind of continue to move a little bit into the bubble wrap, and it'll eventually come to rest. But the bottom line is, it'll take longer for the object to come to rest than the box. So the box might not look that great coming out of that getting dropped, but the thing inside might still be perfectly okay because it took longer because of the bubble wrap and its give to bring the object to rest, and that meant there was less force transmitted into the object inside the box. So this thing about being soft, the key thing that you would want to bring up from a physics perspective is the time factor. That things that cushion or are soft have this ability that Levi mentioned initially to yield or give when something presses into it. And when that happens, it extends the time of some event, and that ends up reducing the amount of force that acts in that event. And so things are less likely to break, and we would say that that makes the scenario safer, okay? So most people summarize this with well, it cushions it. But this is the physics of this idea of cushioning. Okay, we'll see how much of that came through for those of you out in video land. But truth is, most of you are here today, so that's good. All right.